Okay, y'all, we're on the home stretch to Faraday's law. Let's start with a really quick review. Here is the equation for magnetic flux. And this is not Faraday's law, by the way. Now, let me just write that in there. We'll get to that in a minute. But I want to summarize what the equation for magnetic flux tells us. It tells us that the flux through the loop increases based on three different things. It increases with an increasing area of loop. So if the area up here, this equation, increases, then the flux will increase. The flux will also increase, so the flux here will also increase if we have an increase in the magnetic field strength. And you'll also increase the flux through the loop if you align the magnetic field with the normal to the loop. So if this angle theta is 0, then the flux will be at a maximum. And if that whole normal to the loop thing is a bit new to you, you're a bit confused, what this is actually saying is that if the magnetic field is perpendicular to the plane of the loop, so if the loop were representing a plate, that the magnetic field will be perpendicular to the area of that plate. Okay, so now this is the actual Faraday's law. Terrible arrow. Here we go. That's Faraday's law. Up in lights. Faraday's law states, now listen to this, that the EMF induced in a loop is equal to the negative rate of change of magnetic flux. I'm going to say that again and I'm going to write it down. So there you go. The EMF, or the voltage, so the push for the charges in that loop, the EMF induced in a loop is equal to the negative rate of change of magnetic flux. Simple, eh? I'm going to go through that again. I'm going to write down the equation that summarizes this statement. So this equation summarizes Faraday's law. It's saying that if we have a change in flux, now remember that flux over here is dependent on the magnetic field strength, the area, and the angle between the magnetic field strength and the area. So if we have a change in flux, or change in any of those variables over time, so if it's changing with time, then we get an induced EMF, or an induced voltage. So in a loop of Y, what that really means is those electrons are getting a push just as though they were attached to a battery, and so the current will be produced in that loop of wire. The total EMF, or the total push, will be dependent on how many loops there are in there as well. And this negative we're going to get to in the next couple of videos, or the next videos that I'm going to get you to watch. I'm not going to worry about it right now, other than to say that it indicates that nature hates change, and that the induced voltage will allow this law, or allow the processes that are going on to be consistent with conservation of energy. So we'll get to that when we talk about Lenz's law. So basically what I want you to realize is that if we get a change in magnetic flux, or a change in the magnetic field or the area, or the angle between the magnetic field and the area as a function of time, so if it's changing over time, then we'll get a current or an induced voltage in that loop. One other thing I just want to point out before we finish up with Faraday's law here is that you can see here that if your time that these things change over is very small, so if this number down here is really small, then the size of the induced EMF, or the induced current, is very big because they're inversely proportional. So that means if something happens really quickly, so it's happening over a very short space of time, then this change, the delta phi delta t will be very large, which means the induced voltage and current will be very large. Let's get back really quickly to those observations of induced current that we saw a couple of videos ago. Okay, here we are back at observations of what induces a current in a loop of wire. And we've got Faraday's law. Here's Faraday's law here. And of course the definition of flux. So if we look at this summary of observations here, what makes the current go up? Well, they observed that if you quickly changed the magnetic field, so if the rate of change of magnetic field was large, then the current would go up. And yes, magnetic field controls the flux through a loop of wire, and if you change the flux rapidly, you get a voltage induced. Same for if you change the size of the loop. If you change the size of the loop quickly, the area of the loop determines the flux. It's proportional to the flux, and if you change the flux quickly, you get an induced voltage, an inducing current. If you change the orientation of the magnet, so how quickly that changes, or if you move it around even, if you're changing the orientation of the magnet, you're actually changing how many magnetic field lines are going through that loop, how many are piercing the loop, so you're changing the flux. And if you're changing the flux over time, you get an induced current. But what about this moving the magnetic field away? What about if you're moving the magnet away or towards the loop itself? Well, if we go up here and you move the magnet away from or towards the loop, we know that the further you get away from the magnet, the weaker the field is. So actually, as you're moving it away or closer, you're changing the magnetic field. And look, magnetic field determines the flux, and if you're changing the flux over time, you get an induced voltage. And if you have an increased number of loops of wire, what you actually see is this result compounded. So the more loops of wire, the effect is multiplied by how many loops there are. So there you go, Faraday's law in a nutshell.